Simple machines make work easier. They increase the efficiency but does not multiply the energy. It makes work easier because it changes the effort force needed. It also changes the distance in which the effort force is applied. It can also change the direction of the force or change the velocity at certain power levels. However, it cannot amplify force and distance at the same time. So that means if the force increases, the distance can't increase at the same time. You have one or the other, because if you have both, it violates the conservation of energy. So in general, it does three things. It multiplies the force, or it multiplies the distance, or it changes the direction of the force. So you could have one of the three at a time, but you can't have all three at the same time because it violates the conservation of energy. And the work input must always equal to the work output in an ideal situation. There are 6 types of simple machine: levers, wheel and axle, inclined plane, wedge, pulley, and screws. So simple machines increase efficiency by increasing the mechanical advantage. It determines how useful a design is. It is how many times the machine that you made multiplies the effort force. There are 2 types of mechanical advantage. First one is the ideal mechanical advantage. When we have the ideal mechanical advantage, we do not build anything. We just measure and calculate. So in the ideal world, we know the effort force is going to increase and there will be no friction present. So it's 100% efficient. Actual mechanical advantage is what happens in the real world. So you must build it and you must measure the effort and resistance force to determine the value of the mechanical advantage. This is what really happens in real life. So friction will be present, and if you build it correctly, it will multiply the effort force. So the ideal mechanical advantage is equal to dE, which is the distance of the effort, over dr, which is the distance of the resistance. The resistance is also known as load, or the weight that you are lifting or pulling or pushing. AMA is the actual mechanical advantage. It is Fr, which is the magnitude of the resistance force or the load force over the effort force. And the effort is always the input force. It is what you put in to get the machine to work. So when AMA is greater than 1, that means the input force is amplified or it's multiplied. When AMA is equal to 1, it only changes direction. Example of that is a pulley. If the AMA is less than 1, it multiplies the distance or increases the distance. Work is force exerted over a distance in which force and distance must be parallel. So force parallel time distance is work. The units for force is newtons. The units for distance is meter. A newton meter is joules. Power is the rate at which energy is transferred. It measures how quickly energy is transferred. Since power is work or energy over time, the faster you complete your work, the greater the power you will exert, because power and time are inversely related. The SI units for work is joule. SI unit for time is second. A joule per second is watts, which is the SI unit for power. The first simple machine is called a lever. There are 3 classes of lever, which is the first, second, and third, and it is determined by where the effort, force, the load, and the fulcrum are located. The first class, lever, the load and effort are in the opposite sides of the fulcrum. That means the fulcrum is in the middle. Fulcrum is the pivot point. The effort force is on one side. The resistance force or the load is on the opposite side. The distance is measured from the fulcrum to the effort or the resistance. The distance from the fulcrum to the effort is called distance of the effort or the input. The distance from the fulcrum to the resistance force is the distance r, or the distance of the resistance. Example of this are seesaw, crowbars, and pliers. In the second class lever, the fulcrum is located at one end. The effort is furthest away from the fulcrum. The load or the resistance is in the middle. The distance still is measured from the fulcrum. Examples of a second class lever are can openers, wheelbarrow, or nutcracker. Third class lever is the opposite of the second class. The fulcrum is still at one end of the lever. However, the resistance force or the load is at the furthest end, and the effort force or the input force is located in the middle, and the distances are still measured from the fulcrum. The formulas are the same as we discussed previously. Ideal IMA or IMA is equal to distance of the effort or the input over the distance of the resistance or the load. AMA or the actual mechanical advantage is the force of the resistance or the load over the force of the effort or the input. We could solve for one or the other by setting IMA equal to AMA and DE over DR is equal to FR over FE. Remember, load is the same thing as resistance force. Input is the same thing as my effort force. Pause the video and see if you can solve these problems and then check your answer. We have a first class lever in a static equilibrium, has a 50-pound resistance force and a 15-pound effort force. The lever effort force is 4 feet from the fulcrum. So the first thing they want you to do is sketch and label the lever. We know the fulcrum is in the middle with the pivot point because it's a first class. I'm going to draw my effort on the left end. You could draw it on the right end. It really doesn't matter. They just have to be on the opposite ends. So if this is my effort force, this is going to equal to 15 pounds. And then my resistance force or my load is equal to 50 pounds. It's on the opposite ends. And remember, we could flip these. My distance given is for the effort force, which is 4 feet away from the fulcrum. So this is my distance, and this is 4 feet. And this is my DE. And this is what your picture should look like. So what is the actual mechanical advantage? Actual AMA is equal to resistance force over the effort force. Resistance force was given as 50 pounds. The effort force was given as 15 pounds. This will equal to 3.33. My AMA are unitless because the pounds cancel out. It's a ratio. Number 3, calculate the length from the fulcrum to the resistance. So IMA is equal to AMA. We know IMA is going to be DE, the distance of the effort, over the distance of the resistance. We calculated AMA as 3.33. This is equal to the distance of effort that was given as 4 feet divided by DR. So DR is equal to 1.20 feet. Pause the video, try this problem on your own, and then check your answer. Here we have a wheelbarrow. It's used to lift a 200-pound load. Length from the wheel axle to the center of the load is 2 feet. Length from the wheel to axle to the effort is 5 feet. Sketch and label the lever. So since it's a wheelbarrow, this is a second class lever. We know the fulcrum is located at one end. So there's my fulcrum. Here's my lever. Effort is always at the furthest point from the fulcrum, and my resistance is in the middle, or my load. They gave you the load as 200 pounds. This is equal to 200 pounds. Distance from the load to the wheel, from here to here, is 2 feet. And the distance from the fulcrum to the effort is 5 feet. So this is what your diagram should look like. Again, your diagram could be flipped. The fulcrum could be on the opposite side and the effort force can be on the left side. Number 2, what is the ideal mechanical advantage? So IMA is equal to distance of the effort over the distance of the resistance. Distance of the effort is 5 feet. divided by the distance of the resistance, which is 2 feet. This is equal to 2.50. Again, there are no units because it's a ratio. They cancel out. So number 3, we're going to calculate the effort force needed to overcome the resistance force of the system. So we know AMA is equal to IMA. So this is FR over FE. IMA we calculated as 2.50. FR was given as 200 pounds divided by FE because we're looking for the effort or the input force. Rearranging, effort force is about 80 pounds. Pause the video, try this problem on your own, and then check your answer. A pair of 4-inch long tweezers is used to remove a wood sliver. A 1-pound squeezing force is applied to the tweezer. If you move, 1/5 of a pound force is applied to the sliver. It will break and it will be difficult to remove. So the first thing we need to do is we need to sketch and annotate. A tweezer is a 3rd-class lever, so it's going to look opposite of what was in the previous slide. So a 3rd-class lever, again, will have the fulcrum at one end. However, the load will be at the opposite end of the fulcrum, the furthest away. This is my force resistance, and my effort will be in the middle. So my tweezer is 4 inches long, so that means from the fulcrum to my resistance, this is going to be 4 inches. And we are applying a 1-pound force, so that my effort is 1 pound. My effort is 1 pound. And the load force that I want to have is 1/5 of a pound. I don't want to do greater than that because if I do that, it's going to break the sliver and then we can't pull it out. So what is the mechanical advantage? Mechanical advantage is AMA is equal to force of the resistance or the load divided by the input or the effort. So this is going to be 1/5 pound over 1 pound. So this is going to go equal to 1/5, which is equal to 0.200. Number 3, calculate how far from the fulcrum must be held. So we are looking for our input distance to avoid damage to the sliver. So that's going to be IMA is equal to AMA. So that's DE, which is the effort or the input, over dr, which is the load or the resistance. This is equal to 0.200 where we calculated above. De is what we're looking for. Dr we labeled as 4 inch. This is equal to 0.200. Rearranging and calculating, De is equal to 0.800 inch. Wheel and axle is the second type of simple machine. It is 2 circular devices of different sizes attached by a rod. The rod is your fulcrum or your pivot point, and the 2 circular pieces, one will be called the wheel and one will be called the axle, and they will be load and effort. If the wheel is the load, then the axle must be the effort. If the axle is the load, then the wheel has to be effort. The fulcrum is where they are joined together. Example of this is a doorknob, water wheel, or a ceiling fan. The IMA formula is the same as in the levers. It is distance of the effort divided by the distance of the resistance. Since it's a wheel, the distance traveled by a wheel and an axle is the circumference. The circumference of the effort divided by the circumference of the resistance. Circumference is 2 pi r. The 2 and the pi are constants, so they cancel out. So it's just distance of the effort over the distance of the resistance. You could use the radius of the resistance and the radius of the effort, or you could use the diameter. Either or will suffice. AMA is equal to the force of the resistance divided by the force of the effort. The force we are measuring here must be perpendicular to the wheel's surface. This is an example in the picture. The force perpendicular to it is the effort force, but it could also be the resistance force. Pause the video and try this problem on your own and then check your answer. We have an industrial water shutoff valve is designed to operate with 30 pounds effort. The valve will incur a 200-pound resistance force, apply 1.5-inch diameter axle. Sketch and label the diagram. So this is 2 wheels that are concentric circles. We have wheel 1 and then we have the smaller wheel in between, and this is our axle or our pivot point. Our effort wheel must be larger because the input force is less and the resistance force is greater. So the larger wheel is our effort wheel. So we're going to apply an effort force of 30 pounds, and then our resistance force is for the smaller wheel, which is resistance is 200 pounds. So this 1.5 inch is the diameter of the smaller wheel. So this right here is 1.5 inch, and this is my distance R. Part B asks, what is the required actual mechanical advantage of the system? Formula is still the same. So AMA is equal to FR over FE. FR is 200 pounds. FE is 30 pounds. So this is equal to 6.67. Part C, it asks, what is the required wheel diameter to overcome the resistance force? That means we're looking for the diameter of the effort wheel or the input wheel. IMA must equal to AMA. IMA is equal to the distance of the effort divided by the distance of the resistance. This is equal to 6.67. DE is equal to, DE is what we're looking for. Resistance is 1.5 inch. This is equal to 6.67. DE is equal to 10.00 inch. The third type of simple machine is called a pulley. A pulley is a wheel with grooved rim and axle with a rope, belt, or chain around it. Main purpose is it changes direction as well as multiplies the force. There are 3 types of pulley: fixed, movable, and combination. A fixed pulley cannot move. It is fixed to a surface like a ceiling or a table, and it will lift an object up as you pull down on the. A movable pulley is in which one side of the rope, belt, or chain is fixed to a ceiling, and the pulley moves as you pull the object upward. A combination pulley or a compound pulley is one that combines a fixed pulley, which is not movable, with a movable pulley that has an attached load. To calculate the IMA, or the ideal mechanical advantage of a pulley, we count the number of strands or the strings. If it's a combination pulley, we calculate all the individual pulleys itself and then multiply, and that will give us the combination IMA. Pause the video, try this problem on your own, and then check your answer. So a construction crew lifts up 560 pounds of material several times during the day from a flatbed truck to a 32 feet rooftop. A block and tackle system with 50 pounds of effort force is designed to lift the material. What is the AMA? AMA is equal to the resistance or the load over the effort. The load is going to be 560 because they want to lift that much. My effort that I'm going to put in is 50 pounds. So this is going to equal to 11.2. So what is the IMA? Since we can't count the number of strands, we know that IMA is equal to AMA. This is equal to 11.2. Since we can't have 11 strands because we need at least 0.2 and we can't cut the strand to a 0.2, we will need 12 strands. You always round up for pulleys. Pause the video and solve the problems, and then check your answer. Determine the IMA for the following pulleys. If I look at the first pulley, the pulley is being pulled downward. So this rope, even though it's being pulled downward, this is the same rope. So it only exerts one force because all it does here is just changes the direction. And then there's another force from here that's being up. So there's 2 forces up, and we have the weight going down. So if I draw this, we have a tension from the rope, 2 of them, opposing the weight, the load, which is this box, and this is my resistance force or my weight from the load. IMA is going to be 2 because there's 2 strands. So one more time, this first one is one rope. It's only changing direction, so there's only one force pulling it up, and then we have another force pulling this part, the left side up. So there's two strands, so IMA equals to 2. The IMA equals to all the tensions exerted by the rope. So if you know how many tensions are provided by the rope, that is equal to the IMA. In the second picture, the rope is again being pulled down. As this rope is being pulled down, it is the same rope. So this one, it only changes direction. So there's a tension pulling it up here. And then we have two tensions, each pulling up here. So there is 3 tensions going up opposed by one weight. So this IMA is equal to 3. In this last picture, there are 2 tensions pulling it up here. We have another tension from the right rope pulling it up, as well as another tension on the left pulling it up. The IMA is equal to 4. This rope right here, even though this is the same rope, both are pulling up. They exert a tension and they'll divide the force in half. In the first 2 pictures, the tensions were in opposite direction. So all it did was change the direction. So for IMA, it's always distance of effort divided by distance of resistance. For AMA, it is always force of resistance over force of effort. The only difference in the formula is for pulleys. The pulleys are equal to the number of strands or the number of tension forces.